Hello and welcome. Have you ever stopped to wonder if your medicine is really doing what it's supposed to? Well, today we're diving into a super cool field of science that's tackling that exact problem. And it's doing it by, believe it or not, making medicine sticky. It's called mucoadhesion, and get this, it might just change everything we know about how our treatments work, from simple eye drops all the way to life-saving drugs. All right, so here's our game plan. First, we're going to look at a classic problem with how we deliver drugs. Then we'll introduce the sticky solution. After that, we'll get into the nitty-gritty science of how it all works, see how scientists actually test it, and then check out some real-world examples. And finally, we'll take a little peek into what the future might hold.
So let's kick things off with the challenge that, honestly, affects a ton of common medicines. Simply getting the drug to stay where it's needed long enough to actually work.
You know exactly what I'm talking about, right? You put in eye drops, you blink, and poof, they're gone. You can feel them running down your cheek. That is a perfect example of what scientists call poor residence time. The medicine just doesn't hang around. And when that happens, its bioavailability, which is really just the amount of drug that actually gets to do its job, totally tanks. That means you either have to use way more of it or take it more often, and neither of those is a great option. Okay, so what's the fix here? What if the solution was surprisingly simple? What if we could just make medicine stickier?
The whole idea starts with this bigger concept called bioadhesion. And it's pretty much what it sounds like: the ability of some material, usually a special kind of polymer, to stick to something biological. You've definitely seen this in action before. Think about things like denture adhesives or even surgical glues. It's all about creating a bond. But for what we're talking about, delivering medicine to a specific spot, we need to be a lot more targeted.
And that brings us to the real star of the show today, mucoadhesion. This is a very specific kind of bioadhesion. It's when a polymer is designed to stick to one thing and one thing only, the mucosal layer. You know, that wet, kind of gel-like lining you have inside your mouth, your nose, your eyes, and your gut. It's made of mostly water and a protein called mucin. By designing polymers that can grab onto that mucus, we can basically anchor a drug right where we want it.
So this is where it gets really fascinating. How does this stickiness actually work? I mean, we're talking about sticking to a wet, slippery surface. It's not like using regular glue. This is a finely tuned process at the molecular level.
It basically happens in two main stages. First up is the contact stage. Think of it like a tiny, dry sponge hitting a wet surface. The polymer makes contact with the mucus, it immediately starts soaking up water, and it swells up to get really, really close. Then comes stage 2, consolidation. This is where the real grip happens. The long chains of the polymer start to tangle and weave themselves into the chains of the mucus, almost like two plates of spaghetti getting mixed together. They form all these little chemical bonds that lock the whole system firmly in place.
And a huge piece of this puzzle is the polymer size, its molecular weight. Generally, you need a polymer to be at least 100 kilodaltons, which is just a way to measure how heavy a molecule is, to get any decent adhesion. And this chart shows it perfectly with a common polymer, PEG. Down here, at a tiny 20 kDa, you get almost zero stickiness. But look what happens when you jump to 200 kDa. The adhesion strength skyrockets. By 400, it's an incredible adhesive. It just makes sense, right? Longer, heavier chains are way better at getting all tangled up in that mucus network.
But it's not just about being big and heavy. Making the perfect mucoadhesive is kind of like baking a cake. You need all the right ingredients. The polymer chains have to be long, but also flexible enough to bend and weave. They need the right chemical bits on them, these functional groups that act like tiny little magnets to form strong bonds. Even the polymer's electrical charge matters. A negative or anionic charge tends to form a stronger grip. And finally, you need just the right concentration. Too little and it won't stick. Too much and it just gets clumpy and doesn't work properly. Okay, so the theory is solid. The recipe makes sense. But how do scientists actually prove that it works? How in the world do you measure stickiness for something you can't even see?
Well, they do it in two main ways. First, they run in vitro tests, which just means in glass or in the lab. They might do something like literally measure the amount of force it takes to pull the polymer off a sample of animal tissue. Or they might do a wash-off test, where they blast it with artificial saliva to see how long it can hold on.
But for the real proof, they move to in vivo tests inside a living system. They can tag the polymer with a safe radioactive label and then use imaging to watch in real time exactly where it goes and, most importantly, how long it stays there.
So the science checks out in the lab. Now for the really exciting part. Where does the rubber meet the road? Where are these smart medicines actually being used? The applications here are just incredibly broad. You can use this technology pretty much anywhere you find a mucosal surface. Inside the mouth, for instance, you can use a little patch that sticks to your cheek to deliver a drug right into the bloodstream. For the eye, it's the perfect solution to that washout problem we talked about. You could even design a pill that sticks to a specific part of your intestine to release its medicine in a really controlled way. And to give you a sense of the sheer potential, just think about your nose. The surface area of the mucosa inside your nasal cavity is between 150 and 200 square centimeters. That's about the size of a big smartphone. It's this huge area that's rich with blood vessels, making it a fantastic target for getting drugs into your system. The only problem is, normally, anything you put up there gets cleared out in about 15 to 30 minutes. Mucoadhesion can stretch that time out dramatically. And this quote from the researchers really gets to the heart of it. The true power here is that it stops the drug from migrating, from wandering off. And by doing that, you get better therapeutic efficacy. That's just a scientific way of saying it works better. You get much better results, often with less medication. All because you're keeping it exactly where it needs to be for longer.
So this technology is already solving some really big challenges. But as you know, science never just stops. Researchers are already busy working on the next generation, super sticky, even smarter polymers.
And the future looks even more amazing. Two of the big ideas on the horizon are thiolated polymers and lectins. Thiolated polymers, you can think of these as using molecular superglue. They form these incredibly strong covalent bonds that create an ultra-durable anchor. And then you have lectin-based polymers, which are just next level. Lectins are like tiny smart keys. They're engineered to bind only to very specific sugar molecules found on target cells. This opens up the door to hyper-targeted delivery, where a drug sticks only to the exact cells you want to treat.
So when you think about it, we went from solving a simple problem like leaky eye drops all the way to designing the future of targeted therapies. Mucoadhesion is truly changing the game. It makes you wonder, right? Could this seemingly simple idea of sticky medicine fundamentally redefine how we treat disease for years to come? It's a pretty incredible thought. Thanks for joining us.